Hello, I'm Seema and welcome to part 14 of the chapter Hydrocarbons. In the previous video, I told you about conformations in ethane and I told you that there can be infinite number of conformations in the ethane molecule, in the structure. And these conformational isomers have two extremes, the eclipsed conformation and the staggered conformation. This much you know. Let us now talk about how do we represent these conformations on paper. So in this video I'm going to talk about the representation of these conformations, especially the extreme forms, that is the eclipsed and the staggered forms. And after that we'll talk of the relative stability of these conformations. As you know that these two extreme conformations, let me just repeat what they are. If we take one molecule of ethane and I try to make a kind of a tetrahedral structure like this. If you're making it in paper, remember that when you're making a structure in paper, you have only 2 dimensions. So you do not have, 3 dimensions. So you will not be having the tetrahedral angle, rather these 3 angles will be, these 3 bonds would be more or less like the equilateral triangle, going to the corners of an equilateral triangle. So in the Sawhorse projections, when you have the conformations, I showed you in the previous video also, I was actually showing you these Sawhorse projections, that this is the molecule, which is the tetrahedral molecule. This is the carbon-carbon bond. Where they are joining, that is a carbon. And this is the carbon-carbon bond, and these 3 bonds that you see, they are of hydrogens. Yeah, I guess this is more or less. So when these angles, when these bonds are parallel, when you see the front and the back, when they are parallel, the bonds in the front and the back, when they are parallel, the carbon-hydrogen bonds, we call it the eclipsed conformation. And when we twist one of these carbons and these bonds come exactly in the middle. Now the brown one is coming in the middle of the black and the blue, exactly in the middle. That is the other extreme conformation, which is known as the staggered conformation. In the Sawhorse projection, what do? We try to make this structure on paper. So you cannot show this red pen if I make it like this. So what do? We show the red pen in a little slant like this. In a little slant we try to show the structure where this, you can see this bond is the red pen. It is showing you the carbon-carbon bond. These 3 are the carbon-hydrogen bonds on both the carbons. And when you see that this is pointing upwards, this is also pointing upwards, which means these 2 are parallel, these 2 are parallel, and these 2 are parallel. When that happens, that is an eclipsed conformation. Do you see this? When they are, the bonds in front and the bonds in back are parallel, it is the eclipsed conformation. And when they are exactly, the other extreme is, there can be infinite number of bonds between them. And the other extreme is here, where they are exactly in the middle of the bond in the back is exactly in the middle of this angle. So angle that is formed between these 2 bonds. So that is exactly in the middle. That is when you get the other extreme conformation, which is the staggered conformation. So in the Sawhorse projections, the molecule is viewed along the molecular axis. You are looking at it along the axis. You are looking at it like this. And then it is projected on paper, showing you the molecular axis. It is showing you this axis. The angles between these bonds, actually, it is a tetrahedral angle, which is 109 degrees 28 minutes. But since you are projecting it on paper or on board, which is 2-dimensional, you have to flatten it out. So we make this angle 120 degrees. So if you draw a triangle, this would be an equilateral triangle having all equal sides, right? It would have all equal sides, and each tip of the triangle in the center, if you join it, it would make a 120-degree angle. So if you join all of them, 120 plus 120 plus 120 would be 360. So you'll get a complete circle. So all 3 angles are equal and they are 120 degrees, and that is how we make it in order to explain the conformation. So this, you make this 120-degree angle, and if the lines are parallel, in the front and the back are parallel to each other, it is the eclipsed conformation. And if they are in between, now you see this is going on top, but it is falling in between these two. If you make a line on top here, it will fall between these two. So it is exactly dividing the angle between these two in half. Or if you take the back one, these two, this one should fall between these two. This one should fall between these two, and this one should fall between these two. That would be the staggered conformation. So that is how it is. The carbon in front, the dot in front is usually the front carbon, and the dot here is the carbon in the back, the rear carbon. That was Sawhorse projection. The second method of projecting or drawing these conformations on board or on paper are known as the Newman projections. In Newman projections, it says that what is the importance of this carbon-carbon bond? This carbon-carbon bond is actually not, even when I'm showing you these Sawhorse projections, what I'm asking you to focus on is only the angles between the carbons and the hydrogens. The carbon-carbon bond is not important because that allows a complete rotation around itself. So really showing this is not so important. So in Newman projection, what was done? This bond, the carbon-carbon bond, was eliminated. It was said that this is not really required. I can explain the structure simply by using these. If each pen is falling behind the other, it is eclipsed conformation. If it is falling between if each pen comes between the angles, in between each angle, then it is which conformation is it? It is staggered, sorry. Staggered conformation, right? So in Newman projections, what we do, the molecule is viewed from the carbon-carbon head-on. You are looking at it from here, from the carbon, and therefore you do not see this bond. The internuclear axis is what you do not see. You do not view it along the molecular axis. You are only seeing the carbon, that is the nucleus, and the other nucleus, the other carbon, is exactly behind it, because the bond in between, you don't see that. So you are viewing it from the carbon-carbon bond head on. So you're not actually seeing the bond, you're only seeing the carbon here and the three bonds. And you can, from this, if you can see the bonds, if you cannot see the bonds behind it, then it is eclipsed. But if you can see them at any angle, you'll get a number of conformations. But if it is exactly in the center, then you get the staggered conformation. So the molecule is viewed from carbon-carbon head-on. The carbon is represented by a dot which is closer to the observer. The carbon that is in front, the front carbon will be this dot which is looking at the observer. The back carbon, the center, you cannot even show because you're only looking at that, and in the back you can only see the bonds. If they are exactly behind this, the pens, as I used pens, you could use a ball and stick or whatever. And in imagination, if they are exactly behind it, then it is eclipsed conformation. If they are exactly in between the other extreme, then it is the staggered conformation. So molecule is viewed from carbon-carbon head-on, and carbon is represented by a dot which is closer to the observer, is the front carbon. The angle of rotation, or this angle of rotation, you can have two extremes. One is where it is parallel, and the other is the angle, it keeps on increasing, is the staggered conformation, which is the maximum angle. So minimum and maximum angle, or the maximum distance between the two hydrogens. This angle of rotation is known as the torsional angle, or it is known as the dihedral angle. The angle itself is known as torsional angle or dihedral angle, and the strain that it causes is known as torsional strain. The strain that it creates. What is the strain due to? I told you in the previous video that after all, every bond is a pair of electrons, and electrons are negatively charged. They repel each other. So the closer you bring something that repels each other, the more the strain will be. Imagine it in human relations. There is someone you don't like. You just don't like a person. And every time you meet this person, something happens and it always ends up in a fight or an argument or something. So what happens? You start repelling, you start avoiding that person. because he's going to spoil your mood. Every time you meet this person, it's going to result in something bad. So you start repelling, you start staying away. Repulsion is nothing but trying to stay away. So when the conformation is eclipsed, the bonds are the closest. At this time, the torsional strain is, you could say, the hatred, right? Or the repulsion. That repulsion is the highest when they are the closest. Imagine there's someone you always fight with, and that person stays very close to you. You'll both be charged. Anytime you'll be on guard. You are ready to fight that person out because you know it is going to end up badly. You are going to have an argument or whatever. So that kind of a strain that develops due to negatively charged electrons if they are too close, and which depend on the angle, that is why it is known as the torsional angle, and that is the reason why it is known as the torsional strain. Strain due to the torsional angle. The closer the electrons are, the more will be the strain. The further away the electrons are, the better it is. I don't like that guy. If he's in the other room, that's better. If he's in the other city, all the more better. And if he goes to another country, I'd be the happiest person. Joking. So now we come to the relative stability of conformations. I told you that these are, when we talk of relative stability, you can guess from the extremes, the two extremes. Anything in between will have the stability between these. These two extremes, one of them will be stable and one of them will be the least stable. So one extreme will be most stable, the other extreme will be least stable. All other conformations will come in between these two extremes. So ethane, in the staggered form, this is the staggered form. In the staggered form, the distance between the hydrogens is the highest, or the distance between the bonds is the most. So what happens? The electron cloud, the cloud of electrons which have bonds are nothing but electron clouds. So the electron clouds are farthest away from each other in the staggered form. They are as far as possible. But in eclipsed conformation, these electron clouds are the closest. The electrons are closest. As a result of electrons clouds being furthest along in the staggered conformation, they would have minimum repulsive forces, because when you don't like a guy and he's in the other room, you don't care. He's in the other classroom. You don't have to meet him. But if that person is, and not only, the other extreme is, not only is that person in your class, he is sitting on the seat right next to yours. That is when the torsional strain is the highest. Trust me. So when in the eclipsed conformation, they are the closest. So this has in staggered conformation minimum repulsive forces. It doesn't care. It cannot see it also. So how does it make a difference? There is no repulsive. Not no repulsive. They are negatively charged. So repulsive forces are there. You still hate that person. Only he's in the other room. So there are minimum repulsive forces. But in eclipsed conformation, the repulsive forces are the maximum. Anything in between the two would have the repulsive forces between these two extremes. Then, due to maximum repulsive forces between the electrons in the staggered form, the energy will be minimum. When that person who is in the other room, and I don't like him, but he's in the other room, doesn't affect me, my energy, I'm relaxed. My energy is the least. I don't have to get all charged up and all, on my guard every moment, because he's not a threat to me. He's not repelling me right now. He's in the other room. So at that stage, we say the energy is minimum. It is the most stable. Whenever energy is less, stability is more. So this would be maximum. It'll have minimum energy and maximum stability. Why? Because this is an extreme conformation. In the other extreme conformation, it'll be the opposite. That here, it is the eclipsed conformation. It has maximum repulsion. In the eclipsed conformation, that guy is sitting right next to me, so the repulsion is the highest, is the maximum repulsion, and not only maximum repulsion, I'm constantly on guard, any moment I'm going to have to fight this person away. So there's maximum energy, and whenever there is maximum energy, there is minimum stability. When you are charged, when you are angry, That is when you have a lot of energy, but your stability is the least. So there is maximum energy, but minimum stability. And how about torsional strain? Torsional strain is the repulsion only. So the tension, torsional strain would be the tension. So when it is staggered form, the tension is the least. Because that person is in the other room, there is no tension. But in the eclipsed form, the tension is the highest. And anything between the two would be, any other conformation would have these extremes, all of these in between these two extremes. Now what is torsional strain? Torsional strain is the repulsive interaction between electron clouds. It is the repulsion between these electron clouds. Its magnitude depends on the angle of rotation between the carbon-carbon bonds. We know this, that the greater the angle, the less is the strain. Why? Because it depends on the repulsion between the electrons. The less the repulsion, the lesser the repulsion, the lesser is the torsional strain. The greater the repulsion, the greater is the torsional strain. Therefore, it will depend on the angle of rotation about the carbon-carbon bond, which is known as the dihedral angle or the torsional angle. I've shown you what the dihedral angle or torsional angle is. Now, this energy, in the case of ethane, between these two, the torsional strain, if you measure it in kilojoules per mole, in the eclipsed conformation and the staggered conformation, whatever the torsional strain is, the difference between the two is 12.5 kilojoules per mole in the case of ethane, which is a very small value. The difference between the two extremes is only 12.5 kilojoules per mole. And that is the amount of strain between, and all other conformations have energy between these. So that is between whatever those two values are, it will be between those. But that largest difference is 12.5 kilojoules per mole, which is normally what happens when you have that kind of a strain, this can easily be overcome just by a few collisions. You know, if this person with whom I have so much of strain, whether he was in that classroom or he's sitting right next to me, I don't hate him too much. And the strain is not really so high when he sits next to me. So when you don't hate someone so much and you don't hate so much that it doesn't make so much of a difference, just 12.5 kilojoules, then what happens? You don't bother so much about this person. Your friend on this side may interest you more. So you would spend your time talking here. So this strain, by simple collisions, instead of bumping into this one, why not bump into this friend and talk to him, and that makes things easier. So this strain can be overcome by simple collisions of molecules. That little energy difference can be overcome by just collisions or the movement, kinetic energy of the molecules. So in ethane it is 12.5 kilojoules per mole, which is normally overcome by collisions even at ordinary temperatures. It doesn't have to be a special day. Even on a regular school day, you may talk to your other friends, and you may be involved in another thing. Maybe a teacher came, you're busy studying chemistry from me, and therefore you do not pay attention to that guy sitting right next to you. So that reduces the strain that can be overcome. Ordinary temperature, as the molecule gains this much thermal energy, this much thermal and kinetic energy by simple collisions. Thus, it can be said that rotation about the carbon-carbon single bond in ethane is almost free for all practical purposes. So, although we know that there is a torsional strain of 12.5 kilojoules scientifically, or if you calculate it, but since it can easily be overcome, it is not really so significant. It is not, we would say, even though there is a torsional strain, it really doesn't make a difference. They still get along, they still manage together, right? So we'll say that this angle, we said there is a torsional strain. It cannot freely move around each other. You remember in the previous video I told you that although we say that the bond is free to rotate, yet it is not so free, because the staggered conformation will be favored because it is more stable, and the eclipsed conformation would not be that favored because there's too much repulsion in that. But the truth is that the difference between the energy is so less that you will see both the conformations, so it is not the main factor. So we say, for practically, we'd say yes, of course, yeah. It may be a little more partial towards staggered conformation and less partial towards the eclipsed conformation. Yet for all practical purposes, the bond is free moving. It can rotate freely. And that is the reason why, since the the torsional strain is so less, you cannot really differentiate. It is not easy to separate the two conformations, extreme conformations, and of course the other infinite number of conformations of conformers of ethane. So you cannot isolate these. They remain in a mixture. You will have all kinds of conformations. So this was conformations in ethane. With this, I'll wind up today's video. If you found it helpful, give it a thumbs up. Subscribe to my channel, recommend it to your friends, and please keep returning for more videos on chemistry. Thank you for watching, and bye-bye for now.